I guess that's an old-fashioned word, isn't it? Taping. We're not really taping. We're not using a tape.
Yeah, recording.
We're recording. Yeah. Okay, so today we're doing another really cool topic, shear and bending moment diagrams. Everything that's graphical and drawing, you can see I just really love that stuff. But before we get into that, we're going to talk about failures and loading conditions. So we're going to relate it to engineering first to start. So can everybody see this on my screen? Should I zoom in or is it's clear?
Good.
Okay, so what I'm showing here is this is a pin. So here's the pin right here. And I'm showing this in 3D. Usually we'll see this, right? We'll see a strut or a two-force member, and we'll see this, right? We see it in 2D, but I'm drawing it in 3D instead. Here's a pin in 2D. What's going on here is here we have this strut or two-force member, and it has a hole here. And then this is the connection to the ground. So this is all the ground here. So it's three-dimensional. So this is fixed to the ground. And notice that the pin goes through both members, right? Doesn't this make sense that this is what this would look like in 3D? You want me to zoom in a little?
It would help me if there's a horizontal line from the back right corner of the back support and interior.
This right here is the pin that's going horizontally through this little piece that's attached to the ground and through the strut. So I'm looking at this pin right here. And for the pin, of course, this is scrap because if I was drawing a free body diagram of this member right here, I would, and this is point A, I would draw an AX and an AY. And I'm calculating what the X component and the Y component is of the reaction of that pin support. So we see something like this. Okay, so let's just say I get 100 pounds for AY and I get 50 pounds for AX. In the end, as an engineer, we need to design what type of the pin that we're going to choose, right? And we could think of this in terms of strength of material. This pin, I'm going to have control of two different things: the type of the material I'm choosing and the size of it, right? So those of you who are taking material, is steel or aluminum stronger? Or those of you who are not taking materials?
Steel.
Per volume or per weight?
Steel is stronger. Steel is stronger. I'm not asking per weight, Jason. Don't complicate things. I just said strength. Strength is a measure of stress. It's force over area. Okay, so steel is stronger. So if you get a steel one, it would be stronger. But of course, if this is outside, it might corrode. And we're not getting into a discussion of corrosion, Jason, either. Okay, the other thing to determine strength is if I pick something bigger, the material still has the same strength. But if I choose something bigger, it might be able to withstand more. So let's say I calculate an AY of 100 pounds and an AX of 50 pounds. And I'm just going to start from the top. So Amani, what load does this pin have to be able to withstand? We calculated the AX of 50 pounds and the AY of 100.
So 150 total.
Okay, so the first answer somebody would say is, well, it's got to withstand the larger of the two. But think of this, Amani, this is the X component of the force. This is the Y component of the force. So what is A? What is the actual resultant of this force?
Isn't it that adding both of them?
Not adding them.
quick.
I'm not gonna just add them both. What do I have to do? I have to do Pythagorean's theorem, right?
Yeah. Yeah.
Okay. And if you did Pythagorean's
root 'em.
theorem, you should get 111. Did somebody get 111 pounds?
I got it.
Okay, great. So that means now, Amani, wouldn't you say that this pen needs to be able to withstand 111 pounds,
Yep.
right? If you picked a pen that only could withstand 100 pounds, this pen would break. Do you agree?
Yes.
Okay. So now in engineering, we don't just design something for the actual load it's going to take. We actually add a factor of safety, and it's SF is safety factor or factor of safety. So let's say we add a safety factor of 4. Amani, still with you. What load must it take?
115 pounds?
Uh,
Or
no,
is it
it's a
each?
multiplication.
Oh,
Actually, it's a
440.
multiplication. A
okay.
safety factor is multiplied, so it's 111 times 4. So it's 440 pounds, right?
Yep.
Adding is the
Okay.
redneck factor of safety.
Say it again.
I said adding is the redneck factor of safety.
Okay, I don't really know what that means, but
It was a bad joke.
Derogatory.
okay. All right, it's derogatory too. All right. So, and you could imagine in engineering, the higher the safety factor, the more cost of something, right? Because if I'm now designing this to hold 400 pounds instead of 100, I'm going to have to make it beefier. What you make a safety factor higher when you have unknown conditions. So I worked as a geotechnical engineer, and if I'm designing a foundation, I'm not going to dig up all the soil to see what it is. I'm just going to pick some spots to figure out the soil, but I don't really know exactly what's in there. So in geotechnical engineering, the safety factor is much higher because there's a lot of unknown conditions. When you send something in space, although you want to be real safe, you're not going to pick a high safety factor because you don't want to spend as much money. We're talking with billions of dollars. Okay, in any event, we start with a pin. We calculate what the forces are in that, the reactions at the support due to the loading on this strut. Not add in, even the word is like add in a safety factor. Maybe Amani, that's where you added it. You say you add in a safety factor, but you're actually multiplying it. You find out how much it has to carry, and then you go to the tables. And I don't have a steel manual here where I am, but take a look at the table. A table typically says the pin type, so it might be the material. We also might look at the pin size, and then it'll say what the allowable loading is. So if it says 50, 100, 150, let's not put that one there. Let's say this one says 450, this one says 300, this says 250, this says 550, this says 300. We then know that because we have to make sure that it handles 444, we know that this pin and this pin would be allowable for us to use. Okay, so it would tell us the pin name, the number, the material, and the pin size. So I'm just giving you an example of what it would be like once you do the calculation and you choose the pin. You're going to see this in junior level classes. This is outside the scope of statics. What's your question, Jason?
This is shear loading, and it would be distinct.
Yes, I didn't talk about that yet. Okay, I just wrote loading. Okay, so now ready to go into the next step. Let's look at trusses first. Now let's look at loading, complete loading first. Okay, so I'm at the top of this page right now. Everybody could read this. Okay, so we're going to talk about loading and we're going to talk about failure modes. So I took a very slender rod and I applied a force at the end, pulling it. So Angel, When I pull this rod, what is that called? Tension or compression?
That is tension.
Tension, because I'm pulling it apart. When I have, this is a picture of a concrete cylinder. And in this case, I'm applying the load like this. And what is this, Bon?
That's compression.
Compression. So in this case, I'm looking at both tension and compression loading. And this is where the sample fails. Okay, so here it's circular, here it's circular. This is the area where it fails. It gets pulled apart. And for tension, those of you who haven't taken materials, just think of it as taffy. Okay? So do you notice in both these cases, tension and compression, the F, the force applied, is perpendicular to the area where it fails. So I wrote F is perpendicular to A, the location of failure. This is called normal loading. And normal, you might remember, is orthogonal or perpendicular. So normal loading is when the load is perpendicular to the area of failing. You know, it's helpful when I see your faces because I could kind of read whether you have questions or not. So if you guys wouldn't mind, the more faces I could see, the better. Okay, now everybody comfortable with normal loading. The other loading is called shear loading. And let's take an example. I have two pieces of wood that I'm sticking together with a bolt. And I'm applying a load in this direction on the top wood, and I'm applying a load in this direction on the bottom wood. And in the end, Colin, you here? I don't see Colin. Daniel C. Nope, Danny.
Yes.
Danny, where is this, when I pull the wood this direction and pull the wood this direction, what's gonna fail?
That rod in the between them.
Right, the bolt in between
Yeah,
it.
the
And it's gonna
bolts.
fail right here. Does everybody agree it's gonna fail right here? Notice, so this is the area of failure, but in this case, the force is parallel to the area. This is called shear loading. And you could also call it normal and shear failure. Normal is when the force is perpendicular to where it fails, and shear is when the force is parallel to where it fails. Okay, so now I'm going back to my pin. Everybody with me? Here's the pin right here. And the loading on it is like this. And like, well, it's like X and Y, AX and AY. But in the end, it's really here. It's coming off of this. Where is this pin? Daniel H. I don't see him. Oh, Danny, I already did you. Dave. So how is this going to break? Is it going to be a normal failure or a shear failure?
It's a shear failure of the pin, right?
That's correct.
The forces are perpendicular to the failure point of the pin.
Okay, say that.
Wait,
say
no, I'm
that
sorry.
again.
The forces are parallel to
To?
the failure section of the pin.
The failure surface or the
Failure
failure
surface of the pin.
area.
Okay.
So I have a force going up here, right, of A, and the surface is right here where it's going to fail. It's going to fail right here, right? This is shear failure. Let's think of it like this. Actually, okay, I have a pen. I'm actually separating it in two pieces so I could actually show a shear failure. But I'm applying a force going down and I'm applying a force going up, and the failure surface is right here. So the force, the force direction is parallel to the area of failure. It's a shear failure. Okay, so the same thing is happening here. this pin is going to break right here and it's parallel to the area. So this allowable loading I'm talking about is shear, because I'm looking at a shear failure here. Okay. How about this? What if I take this and I twist it? I'm at David, LR. I'm taking this and I'm twisting this, twisting. What's going to happen to this pen?
It's gonna
Where is
snap
it going to break?
in the middle.
It's going to break right here, right? It's going to
Yeah.
break right here. And even though this isn't a force going down or up, this torsional load that I'm applying, does it look more like a normal failure or a shear failure?
Like a normal.
Try it again. My load is this way, right? My load is this way, and it's going to fail right here. So this is where it's failing, and this is my load. Does it look like the load is parallel to the surface of failure or perpendicular?
Parallel, so it'd be shear.
Parallel.
Okay.
Parallel. So those of you who have taken a screw off your wheel on your car, right? And you twisted it and you failed it in torsion. You really failed it in torsion, but you call it a shear failure. Torsion is indirect shear, where this here is direct shear. I am applying a force right here. It's parallel to the failure surface. This is called direct shear. Indirect shear is if I have, I'm just going to take a sample. I have a sample and I'm twisting it like this and twisting it like this and twisting it like this. In the end, the failure surface is right here. And this load, let's just call it T for torsion. Actually, torsion is represented as tau. Again, this is all outside the scope of this class, but I want to just teach it to you. Torsion is parallel to the area, so it's also considered a shear failure, but it's called indirect shear. All right, so first, we looked at a pin. We noticed that when we calculate AX and AY, the load actually on the pin is the resultant of those two forces, and we would have to choose a pin that could handle that load. And if we did put a factor of safety on it, we would have to make sure that that pin could handle a larger load. And the load we're looking at is a shear load, because the failure that would happen at a pin is a shear failure. Okay, then we looked at two different types of loading conditions, normal and shear. In normal, the force is perpendicular to the area, so both tension and compression are normal, and shear is where the force is parallel to the area. These, you could call them, these are adjectives to loading and adjectives to failure, meaning I could have normal and or shear loading, and I could have normal and or shear failure. Okay, now we're looking at our truss. When we did trusses, Edgar, trusses are composed of what kind of members? They're all the same. What are they?
Two force members.
Two force members. Talk louder, okay?
Yes.
They're all two force members. Which means, what does that mean? Where is the loading in a two force member?
At the at the joints.
At the joints, the load, right, the loads that are put on it is at the joints. And in turn, how do I calculate? I don't calculate a force in the X and the force in the Y in the member. Instead, where is the load inside the member?
Oh, so you mean like instead of having it two forces on the joints, I only have one direction in the one force in the direction of, let's say, joint A to joint B.
Great. So that member turns out to have one force, right? And after we calculate the force, we get either a positive or negative. And what do we assign to the positive?
Tension.
And what do we assign to the negative?
Gotta be compression.
Compression. So that means a two-force member on a truss is either dealing with tension or it's dealing with compression. So what kind of loading is it? Is it normal or shear?
Normal.
Normal. So we were calculating for the pin, we were calculating the shear loading in the pin. For the truss, we're calculating the normal loading. Okay? Well, let's have another example now. These beams we're going to be looking at together. Here's a beam. It has a pin on one end and it has a roller on the other end. And it has external loads of, let's call it F1, F2, and F3. And we'll call this point A and this point B. And Elizabeth, Eric,
Morning.
Eric, great. Okay, Eric, I'm looking at this loading in this beam. If this force, we're always looking at this in static equilibrium, right? So we're
Right.
calculating all the loads that there's no failure at all. Because if there were failure, it would be dynamic, it would break. So we have F1 here, F2 here, F3 here. What kind of loading is this beam experiencing? Is it experiencing tension and compression, or is it experiencing shear?
Shear.
Shear. If this thing breaks, it would break right here in shear. This is the area, the surface where the failure would be, and my force is parallel to that area. So I can have a certain kind of shear failure here. Okay, I'm going to come back to this in a minute. Let's take a look at this example. Here, I have a wall. You just bought a store, a mom and pop store. You have a sign. You chose to put a sign out here. But the only thing you had was huge, big old steel sheets to make your sign. So you put this huge sign here that has a huge amount of weight. Okay. And I'm going to continue with you, Eric. If this weight is too great for this beam, which is actually called cantilever is when you have a connection at the end and all the loads are here. This is a cantilever beam. If the load is really high here and you put a toothpick, you put a huge steel thing here, right? How is this going to break? Is it going to be a normal failure or shear failure?
Shear.
Shear. It's going to be shear. Are you sure? Because you're asking that you answered with the question. I think you're sure. You just said it wrong, right?
Yeah, I was
Because
thinking through it as I said it.
good. So the weight, the load here is parallel to the area surface. So that again, this is a shear failure. Okay. Speaking about cantilever, let me go back to this. And you probably learned all this if you took materials. This is called cantilever. You could tell that if this load was great, wouldn't it start bending? Right? It would start bending. This is a cantilever bend test. This one, it's supported on the ends. And if the loading was really great in the center, you see the beam deflect like this. This is called simply supported. So when you have a horizontal member, when you have a beam that's supported on the ends, it's called simply supported. And when you have a beam that's only supported on one end, you have a cantilever bending. Everybody good? Who's in materials? Did Carl talk about this kind of stuff?
The only levers
Did he
we're
talk
really
about it, yes or
talking
no?
about, no.
Okay. Okay, so let me just say one more thing, you guys, since I'm covering the topic. Take a look at this beam, you guys. We talked about it failing in shear. Take a look at this beam though. If it deflects so much, aren't you going to experience some stretching down here? Because the material is going to start to stretch down below and it's going to compress up top. So even though we're talking about the failure that usually occurs in a beam is a shear failure, you could have cracking on the bottom that would actually cause failure due to tension, because it is experiencing tension stretching on the bottom and it's experiencing compression on the top. That's why when you ever design a concrete walkway, you always put steel rebar inside. Because if you didn't put rebar and it deflected, all the concrete would crack and fail. Okay? But we're going to go back to what we need to know for here. We're looking at the simply supported beam, and we know that with loads that are too great, I can have a shear failure. And the same thing here with the cantilever. If the load is too great, I could have a shear failure. That means it is very important for us in beams, anything horizontal, for us to be able to know what the possibility of shear failure is along the length of the beam. Another thing we need to know is, Gerardo, I see you here. I don't see words though. Are you chatting? No. Okay, Hyoji, Isaac.
Yeah.
Isaac, going back to this situation, I have this cantilever beam with a huge weight here. It may have a shear failure. It could even have a shear failure here. But can you think of another failure that could come? Because a shear failure means it's just broke, right? Like that because of the force. It's breaking because of the force. Can you see something else that could cause a failure?
Bending. And then is
Great,
snapping
bending.
is snapping considered different, or is that considered shear?
Snapping could be due to shear or bending. But
Okay.
basically, this beam could fail and this beam could fail due to shear, right? Due to the loading or due to the loading at a distance. Okay, so what's really important for us to figure out, I wrote here that whenever we're looking at beams, we could have failure due to two different things: shear force and a moment, I'm going to call it bending moment. So I have to worry about shear, which is the variable for shear is V, and bending moment, and the variable is BM, bending moment. So what we're learning today is we're going to be learning shear and bending moment diagrams. So here I have a beam. I have a beam right here. It goes from point A to point B. I have external loads on this beam. The supports are wherever they happen to be. They could be somewhere in the center. And at every point along this beam, I need to calculate what the shear and the bending moment is that it experiences. And if you want to look at it, think back to the truss. The truss, what we did is we broke the truss right here and applied the internal, that loading that was inside became external. We broke the truss member and applied the tension force. In a beam, we're breaking it somewhere and we're calculating what the shear and the bending moment is at every point along this beam. So we have 30 minutes before the quiz. So what we're going to do is we're going to do the shortcut of calculating. We're not going to calculate. We're going to do the diagram straight off. Are you ready? So the two problems we're going to do in the textbook is 38 and 42. So we're going to look at 38 first. And it's on page 387. Okay.
So it may be informative or instructive that VBM seem to go together.
Yeah, well, we calculate them together, but they're two different unknowns. We're calculating the shear, we're calculating the force the beam is experiencing at every point, and we're calculating the bending moment. They're two different things, and they're two different diagrams. But typically you write VBM because usually when you show the shear diagram, you show the bending moment diagram too.
Because
There's
usually
two
a
of them.
structure that has one has the other.
Yeah, well, you'll see as we do it now. So I'm going to 387 and 380, page 387, and I'm looking at problem 37. Okay? And what I'm going to do is you guys draw this on the right side of the paper. I'm going to move my thing out. I didn't bring a clear ruler. I have my mom's old-fashioned ruler here. And I'm drawing a line down and a line down. And I'm drawing my beam across. And for this problem, 38, 7.38, I'm going from point A to point B. And I have point C. I have point E. Point C, point E, and then I have point D. And point D has 300 pounds on it. Point A has 120 pounds. And the other point B has, the other point at the end is 120 pounds. And the distances are 10 inches, 25 inches, 20 inches, and 15 inches.
Wait, isn't
Yeah.
that problem 3.8?
Say it again?
That's not problem 3.7.
We're doing 3.8. This is 3.8, isn't it?
Oh, okay. I thought you said 3.7. Sorry.
Yeah, it was on page 3. It's confusing. It's page 387, and it's problem 738.
Okay.
Okay. All right, I'm going to remove my textbook now. All right. Jack. Hey, Jack, what connection is at C?
Sorry, I'm still trying to find my book. I don't know where it is.
All right, look at the picture here. What's at point C? Can you see it?
Is it a pin?
Yes.
Yeah, yeah.
And what's at E?
Looks like a roller.
Right. So what reactions do we have at C?
X and Y.
Right, CX and CY. What reactions do we have at E?
Just E, Y.
Looking at this, the way it's all loaded, what's CX going to be equal to?
0.
Right. Do sum of the forces in the x, Cx equals 0. Okay, how can I find Cy?
You do some of the moments about E.
Great. Do sum of the moments about E and I get Cy. How do I find Ey?
You could just do some of the forces in Y.
Great. So I'm not doing the math because you know how to do this by now. Some of the moments about E gave us a Cy of 240 pounds. Sum of the forces in the X equals 0 gave us a Cx of 0. And sum of the forces in the Y gave us Ey equal to 300 pounds. And then I did a sum of the moments about C to do a check. So at C, I have a 240 pounds up, and at E, I have 300 pounds up. Okay, you guys, you ready? Got you a little dizzy there, didn't I? Okay, so now everybody sees I drew the beam at the top. I labeled the points. I put the distances and I put all the loads on here. Everybody sees the loads? There's a 120, there's a 240, there's a 300, there's a 300, and there's a 120. Okay, make sure you have enough space and you're drawing a line down here. And this is our shear. And Jason, is shear a force or a moment? Jason Lavoie,
Yeah.
shear.
A force?
Does
or
it have a unit
moment?
of force or does it have a unit of moments?
Well, gee, I love that question.
Okay, let me
I would say,
take a look at this picture. I'm going to calculate the shear force at every point, and I'm going to calculate the moment at every point. So if shear is a force, what are the units going to be?
I mean, newtons or pounds.
Right, but in this problem, pounds, right?
Pounds.
Right.
Yeah.
So I'm going to draw a horizontal
Well, it's interesting because you
line.
had the.
I didn't pin. Can I just pin it on here? Where's my expert, Marcine?
Sorry, what's the question?
I was asking you about how to pin it. I think I got it. Okay, so we have a horizontal line. This line right here, this is the 0 line, and this is positive and this is negative, because we're going to draw a diagram. Okay. And so is everybody ready now? Because I'm going to start drawing the diagram. And then I'm going to do the math, but we'll do the math on Thursday. Today, I'm just showing you how to draw the diagram. And we'll talk about why I'm drawing it the way it is. Everybody ready? Okay, Jason Lee, are you here? Jordan. Laura. Laura, I think you're here.
I'm here.
Okay, Laura. So take a look up top. There's a 120 pound force here. So I'm going to go down 120. So I think what I'm going to do is I'm going to call this 100, 200, because I want to draw it to scale. So this line represents 0. And these numbers right here are in the negative, and these numbers are in the positive. And I have to go down to 120. So that's about 120. So I'm going to write 120. Laura, between point A and C, are there any loads here?
No.
No. So the 120, oh, I forgot to draw my lines. I have to draw my line down for C, draw my line down everywhere there's a force. So Lori, you said that going from point A to C, there's no change in loading. So I'm just going to continue the 120 across. Okay, then Laura, at C, what happens?
There's a positive force.
There's a positive of 240. Notice that the one at A was 120 and I drew it down. What do you think I do with the 240?
You draw it at 120 and the positive.
I draw it up to 120. And then Laura, I'm going to continue. From point C to D, is there any change in loading here?
No,
No, so what happens?
it's going to be continuous to.
Stays the same. Okay, is Liam here?
Yes.
Good, Liam. So stays the same. At point D, what load do I have?
300 pounds down.
Okay, so I go 300 down, and where do I have to stop?
Negative 180.
Right, at 180. And you don't have to write negatives and positives on the diagram because you already wrote it out here. Okay, and then Liam, what happens from D to E? Are there any loads?
No.
So there's no change. Luis, are you here?
Yeah, Joanne.
Okay, what's happening when I hit point E?
You're getting another 300 force up.
Right, so where am I going to?
Looks like 180.
Well, I'm at 180 now, so what do I go up to?
Go up 300.
I have to go up 300, so where do I stop?
Right about there.
Yeah, what is that number?
120.
120. And then, Luis, from D to B, from E to B, is there any loading here?
No.
So there's no change, right?
Yeah.
Okay, and then what happens when I hit B?
You go down.
Go down.
120.
And it closes at 0. Notice all the shear diagram has to start and end at 0. And then what you do is you just color it in. Isn't this so cool? We could visually see the shear loading that is going on anywhere in this beam. Luis.
Yeah, Joanne.
If this is not if this is, this here is one piece of, let's say, lumber. It's a beam, one piece of lumber. And this is the loading the lumber is experiencing. Where does it experience its greatest shear?
Looks like it gets distributed between 300 and 300.
Right, so give me the location
From,
based on the letters. Which section of this beam experiences the greatest shear?
from D to E.
From D to E, right here, it experiences its greatest shear. So if this beam fails in shear, this is where it's going to fail. It's going to fail between D and E.
So you're saying the area would be between D and E? Somewhere.
Yeah, it would be between D and E where it would fail. So, but we don't want it to fail, right? We don't want this beam to fail at all. So, Luis, looking at failure, what is the maximum shear that we have to design? What is the shear that we should design this beam at? What should it have to hold?
A minimum of 180.
Awesome. It must be greater than, let's just say, let's just call it max. 180 pounds.
So when you said,
so you're right that we have to design this beam to withstand more than 180 shear loading, pounds of shear loading. Just like with the pin, going back to the pin, I knew it had to withstand 111. I multiplied it by a factor of safety, and I knew I had to pick a pin that could hold more than 444 pounds. It's the same thing with this. This beam, the maximum shear it's experiencing is 180. I have to make sure that I pick a beam that can handle 180 pounds.
Even if the value is negative?
Even if the value is negative. It doesn't matter whether that's a great question. It doesn't matter if the shear failure, if the failure is going to go down negative or up positive. The point is that it has to be able, this piece of wood has to be able to withstand the shear.
Yeah, it occurs to me that if you were to have started the diagram from the other side and worked your way across, the whole thing would be mirrored about that horizontal
That's
line.
correct. And that makes sense because it's the same thing as doing trusses with sections. With sections, the left side has the equal and opposite loading of the right side. So it's the same thing here. If we looked at the shear diagram going the opposite side, we'd get the negative. But we always do shear diagrams from left to right, and we always do moment diagrams from left to right.
Yeah, Jason, I was thinking the same thing, but I think you get the same result. You would say the maximum is 180 between D and E. It would still be
Correct.
the farthest in that same section.
That's correct.
So is the positive and negative just kind of like a guide to tell us?
It doesn't matter.
Okay.
You know, think of it this way. If your ruler is too small or too big, it doesn't matter if it's too small or too big, it doesn't work. It's an error. If you're surveying, those of you who took surveying, if you're off by a foot, if you're short a foot or over a foot, when you put in a building, you screwed up. A negative and positive doesn't matter. It doesn't matter. You have to design this to handle a shear. So the textbook actually calls it absolute value of the shear, but other textbooks I used have never said that. They never said absolute value. Oh, and speaking of absolute value, Dave, I remember that I had spoken to you that I said I was going to do that little video. I hadn't done it yet. Okay, you guys,
no
next.
biggie.
I'm going to get rid of these arrows and I make sure my line, and now I'm going to do another horizontal line. And now I'm doing the bending moment. And usually I just call it M. This is 0, this is positive, this is negative. What units? So we're Luis Mackenzie? Marcine, what units are is the moment?
Inch pounds.
Right, inch pound. Okay. So everybody's totally comfortable with this, right? Force goes down, shear goes down. Force goes up, shear goes up. Force goes down, shear goes down. No problem. Let's do something up here. Notice this is a negative area. This is a positive area. This is a negative area, and this is a positive area. Do you remember with distributed loads, what is the moment equal to? It's equal to V dx. Oh, not V, I shouldn't say V. It's equal to the force dx, right? So it's equal to the force times x. It's the area. The moment is equal to the integral of the shear. It's the area of the shear diagram. So Marcine, let's do this. What is the area here?
It's gonna be the 100 times, is it the length of the
Beam.
Yeah.
Did you notice I just numbered these sections 1, 2, 3, and 4? So the area of section 1 is 120 times 10. So it's 1200. Area of 2 is 120 times what, Marcine?
25?
25. This is inch pound, right?
Yeah.
What's 120 times 25?
3,000.
Thank you. Area of 3. Keep going, Marcine.
That's the one, I think that's 180 times 20.
Right.
And that's
And the last one is
120 times 15.
right. Okay, so this is 120 times 15 is what?
1800.
1,500?
1800.
1,800, thanks.
And the other one
And
is
then-
3600.
Great. Okay, so I got the areas. If we're doing an integral, notice the line that's here is this line, this line, this line, this line. So if this is a negative area, you guys are really comfortable with math. This is a negative area. What do you think the slope is here on the moment diagram? Marcine still?
I'm sorry, what was the question?
This is a negative area.
Yeah.
What do you think the slope? Do you think the moment diagram is going to go up or go down?
Is it going to go up?
It's going to go down because it's a negative area.
Okay.
So it's going to go down to 1,200. I'm going to call this 1,000, 2,000. And I'm picking these numbers because I'm figuring out what it's going to be. So for that first section, it's going to go from 0 to 1,200. Here's 1,200. Good. So notice, and I could color this in if I wanted. Usually I color in at the end, but we could color it in now. So is everybody getting this? The area here is negative. So our slope for our moment is negative. So Marcine, the next area that you calculated as 3,000 is positive. So what do you think is going to happen here?
It's going to go up.
Yep. And it's going to go up to what?
Up by 3,000.
Right. So what is it going to go up to? It's at-
1,800.
Right, 1,800. Okay, Marcine, Maria, now what happens? I'm at 1,800 positive. There's another negative area and that area is 3,600. What should I do?
Now you're gonna go down by 3,600.
Right? Where am I gonna end up?
I think at 1,800.
Yep. Okay, and Maria, last one. The next one is a positive area. The positive area was 1,800. And what am I going to do here?
You're gonna go up by 1,800 to 0.
Right. Matthew, is Matthew here?
Yeah, I'm here.
Okay, Matthew. So what is the maximum moment that this beam experiences?
The 1,800.
Right. And it's in both spots, right? So if it fails in moment, where do you think it's going to fail?
Well, either of the 300 pounds.
Yeah, but let's talk about points, okay?
Yeah,
What
so that would
points?
be point D and point E.
That's correct. So if you have failure between D and E, the failure, so let's say you designed a beam and 5 years later it fails. And it fails right here. You guys, it fails right here. What would you say the failure mode is? Matthew? So you have a beam, you designed it. In 5 years, it fails right here. What is its failure mode? Did it fail in shear or in moment?
It failed in shear.
Correct. If it failed at point D or E, then it's quite likely.
It failed in moments.
Moment, it could be shear, right? Because shear covers all D to E. Okay. So now you know where the failure is most likely to occur. If it fails somewhere else, there might be a problem in a you know, there might be some heterogeneous material and there's some problem somewhere else. But so now let's just go back to this. So what we're given is we're given a beam with all the external loads on it. And the first step is to draw the beam, right? So the first step is draw the beam with lots of space below it. And the second step is to determine what the reactions are at the supports and put them in the beam. Third step is to draw all these vertical lines. The fourth step is to draw the horizontal line at the shear and make sure that you write V, 0 plus or minus, put the units. And then you go through, goes down 120, up 240, down 300, up 300, down 120. And from seeing what these numbers were, I knew what I wanted to make the scale of my drawing to be. And then I calculated the area of the shear diagram. And then I was able to draw my moment diagram. When the area in the shear was negative, it went down. When the area of the shear was positive, it went up. And from these diagrams, I can see where this beam experiences its maximum shear and where it experiences its maximum bending moment. Okay, questions? I'm going to unpin this now. I don't know how to do that. Let's see. Okay, questions?
Why is it called V? Why is she?
I don't know. I'd have to look it up. I don't remember.
Okay.
Shear, I don't know. It's kind of like, I don't know. It's just natural to me now. I don't even think about why. So I should look it up. I don't know. Somebody picked it. Maybe Mrs. Shear. Mrs. V.
Well, I was gonna say
V
maybe it's
looks-
Mrs. Victoria, and that's why she named it like that.
That's right, Mrs. Victoria.
Anyway.
Or V looks like the leading edge of a shear.
Shear failure. Who knows? Okay, everybody comfortable? Okay, so notice the only problem I did so far had all point loads on it. So I posted the homework already. I posted the solutions already. You can go ahead and do the problems that only have point loads. The next problem we're going to do on Thursday has distributed loads because we need to be able to calculate draw the shear and bending moment diagrams for distributed loads too. Okay, but I want to show you some things on the page. So I'm not quite sure if this is going to show up on the video, but could you guys, oh wait. Can you guys see my screen?
Yeah, that's good.
Okay, so look at this, shear and bending moment standards in the steel manual. So I didn't have my manual with me, but I did have photocopies from it. So I'm gonna open this up. Okay, can you see this? So this is the 8th edition. This is from the 80s, you guys. So we're probably on the 20th edition now. Okay. I know you have to look sideways. I guess I could turn it. Let me turn it. Look at this. This is really cool. They have all these standard loading conditions. This is the loading condition, which represents the beam with supports on the end. This is the shear diagram, and this is the moment diagram. And then it gives you the values. Let me see if I can make it bigger. It gives you the values for what the maximum moment is. It gives you values for what this delta is, a deflection that a beam can have. So let's take a look at These are all showing ones with distributed loads. Let's take a look at, let's look at this one. So here's a loading condition where you have simply supported on the ends and a point load in the middle, and L represents the length, and then they show you what the shear would be. And V here represents half of P. And that totally makes sense, because if this is P and it's in the center, then each R is going to be half of P. So you're going to go up P over 2. And then they have another one here. So these are really cool. There's a whole mess of them in here. Look at this. There's like 10 pages of them. So you can take a look at these if you want.
I
Okay,
can't
I'm gonna,
believe it. It's a practical example of calculus.
Yes.
Word.
Yes. But we're not going to use calculus to do it.
But like anyway, it's a theory
It is
application.
it is calculus, but I'm doing it not by integrals. Right? Okay. All right. Let me stop sharing. No, I don't want to stop sharing. I want to go back to the module. So I did not do the overview yet, and you'll see it's not even published. So maybe we'll do that on Thursday. I like doing it together because we could talk about words together. Here's a shear and bending moment diagram template. Let me open it up. And you don't really need a template, but here it is. I basically put the shear, the units, plus or minus. There's the bending moment. So here's the template. Here's a summary of converting all the integration to graphical, and I'll show you that on Thursday. Here are some standards, and then here's your homework assignment. Okay, so right now I'm ready to start the quiz. So before we do that, let's just check in with everybody and see, does anybody have any questions about the shear and bending moment diagrams yet? So if I gave you any problems that did not have a distributed load, you could do it. Okay, I don't remember what the problems, they might have all had distributed loads, then just wait. But are you ready to do, does anybody have a question on shear and bending moment diagrams? No. Okay, so let's start our quiz. Hey, Matthew, is that the King Arthur?
Oh, it's
sword
Legend
in
of
the back?
Zelda. Come on, it's Legend of Zelda.
Oh, I got it wrong too.
I mean, it's kind
Sorry.
of a modern take of it because the hero still has to pull the sword from the stone, and only the chosen hero can pull it. So it's got a similar
Okay.
feel.
But now a magic tree tells him to do it.
Oh, really?
Only in this version.
I guess you're right. Yeah.
If you have time free in January and you have, brothers and sisters that are, teenagers or even like 8, there's this TV series that was on called Merlin about the King Arthur time. It's so awesome that it's the King Arthur time where no one's supposed to have magic, but Merlin has magic and he has to hide it. And it's great. It's everything. Strong women characters.
You don't have to be 8 to
adventure,
appreciate
love.
that.
What?
You don't have to have the excuse of having a small
Right.
child to watch that. You could
No,
be an
you can
adult and
watch
watch
it.
that.
Yeah.
Sorry. Did you guys see it, Merlin? I loved it. Anyway, all right, let's do the quiz. So I'm going to share. Okay, quiz. So let's take a look at it. Oh, you're not going to be able to see it now. Hang on a second. I got to stop sharing. Okay, so this is the trust quiz. It says, determine the force in each of the following members, CB, CD, CG, CH, and be sure to specify whether they're tension or compression. You guys, spend a little time looking at it before you do it. It should take you less than 15 minutes to do this problem. Okay. Okay, go for it.